Hello, this is Mr. Doro. Today we're going to be talking about solutions. The objective for today is that the student will be able to identify the parts and properties of a solution and describe what happens during the solvation process. I want you to know that this is, if you're in honors chemistry, then this is going to be in chapters 12 and part of chapter 13 in your book, and in general chemistry, this is in chapter 16 in your book. This is a definition of a solution that you're going to need to know. It's a homogeneous mixture of two or more substances that exist in a single phase. Single phase means that they're all in one state when they get done. Homogeneous mixture is different from a heterogeneous mixture. Heterogeneous, they're in there together, but they are not evenly dispersed. Homogeneous, they're in together, not chemically bonded with each other, but they are evenly dispersed all the way throughout, and that's what a solution is, a homogeneous mixture. The parts of solutions that you're going to have to know are a solvent. Solvent is the thing that does the dissolving, and a solute is the thing that gets dissolved, or the dissolved substance. If you look at our little picture right here, then we'll say this is water. Water would be the solvent, the thing that does the dissolving. The solute is the thing that gets dispersed throughout. We can have many different types of solute and solvent solutions. One of the types that we can have is a gas solute and a gas solvent. And this is an example of one right here. This is, we can think of it as oxygen in nitrogen. And so you can see that we have a bunch of different molecules of the gases. And remember, gases are always moving around every which way. But you have a mixture in here. They're not chemically bonded with each other, but they will be evenly dispersed. Even though it doesn't look evenly dispersed, this is on a very, very small scale right here. And so it would be evenly dispersed for us. You could also have a gas dissolved into a liquid. This picture over here is showing molecules of carbon dioxide gas dissolved in water. And you can have carbon dioxide dissolved in water. You can see the water is surrounding it, and that would be the gas dissolved in the liquid. Overall, it would just look like a liquid. You could also have a liquid dissolved in a liquid. I don't have a picture of one, but you've seen liquids dissolved in liquids before, like vinegar in water or alcohol in water. And so the overall phase would just be a liquid when it gets done. And then you could have a liquid and dissolved into a solid. And so here is an example of a liquid dissolved into a solid. This is dental amalgam. This is mercury and silver and tin. The mercury was a liquid dissolved into the silver and into the tin to make a filling for a cavity. And then you could also have a solid dissolved into a liquid. This is normally what we end up dealing with here. This is sugar and water, and you can see that we have the liquid and here's the solid. As we mix it up, we make a sugar solution and ends up being yummy. And then we also could have a solid dissolved into a solid also. This is an example of a solid dissolved into a solid. This is copper in nickel, and so it is a copper-nickel alloy. And so two solids, of course, they have to melt it down to do that, but then they are solids dissolved into each other. There are also some other types of mixtures. Now, these are both heterogeneous mixtures. They're not solutions, but colloids are heterogeneous mixtures. They have particles that are a little bit bigger than the solutions, but they're still small enough to stay dispersed. And there's a lot of different examples of colloids, things that you know. There's gelatin, like Jell-O is a colloid, mayonnaise, shaving cream, fog, cheese, butter, aerosol sprays. There's a lot of things that end up being colloids, and they stay dispersed. The particles stay dispersed. They're small enough to do that. Suspensions are a little bit different. Suspensions have the largest particle size of the three, and the particles do settle out over time. So you can think about this as muddy water. You could shake it up, and it would end up being muddy for a little while, but then eventually the dirt ends up going to the bottom, and you could filter out those larger particles. So that brings us to the fundamental rule of dissolving, and that is that like dissolves like right here. You need to know this. Polar things will dissolve other polar things. Nonpolar molecules will dissolve other nonpolar molecules, and usually that's the way it ends up happening. That includes ionic compounds are polar because they have a positive end and a negative end, and so that's why water will dissolve things that are ionic compounds so many times. There are a couple terms to describe solutions as either electrolytes or non-electrolytes, and we're going to talk about what an electrolyte is. An electrolyte is, what it is it will conduct electricity. And a non-electrolyte does not conduct electricity, of course. So what makes things an electrolyte and a non-electrolyte? Well, if you look at these solutions right here, this is just a distilled water solution, just pure water, and it is not lighting up the light bulb. This one is a salt water solution, and the light bulb is lighting. Now that has a power source. It is just these probes are down inside here, and they're allowing the charges to flow back and forth between the probes. And this one is a sugar solution, and you can see that that one's not lighting, so we're going to see why that happens. We can better understand if something is an electrolyte or not by thinking about the process of solvation. Solvation is also called dissolution, and it's what happens when you put something into a solvent, a solute into a solvent, and see what happens to that compound. Now, there are two different ways that you can have this. This one right here that we're looking at is sodium chloride when it's put into water. Sodium chloride is an ionic compound, and so what ends up happening is this. The sodium chloride, NaCl, breaks apart, gets broken apart by the water into sodium ions, Na+, and chloride ions, Cl-. And those get surrounded by waters. And so if you look at this picture right here, you can see that this chlorine right here is surrounded by the positive hydrogens on this in the water. The hydrogens are all facing the chlorines. And the oxygens, the negative oxygens, are facing the sodium ions. And so really what happens is when you put these in solution, these break right apart. This is called solvation, and when they make these positive and negative charges, that allows, when you put these probes in there, then that allows the electricity to flow through from one side to the other, and that's why the light bulb was lit up. Now here's another picture of it. Sodium chloride, this is salt, and you put this in water, and here it is. You got the chloride ions and the sodium ions, and you get those positive and negative charges. The more of those you put in there, the better it will conduct electricity. Now this one down here though is a sugar solution. Sugar is a molecular compound, and it does not break apart into the ions. It just breaks apart into the sugar molecules, and they get surrounded still by water molecules. The positive attracts the negative ends, and the negative attracts the positive. So if you have an ionic compound getting dissolved in water, then it will end up being an electrolyte because of the charges. If you have a molecular compound, it does not end up an electrolyte because it does not make charged particles. It just breaks apart into the individual molecules. An important aspect of dissolving is solubility. Solubility is how much of the solute will dissolve in a given amount of solvent. So if you look at the graph that I have right here, this is, on this side, it is the grams of solute per 100 grams of water. So all of this is in 100 grams of water. It doesn't change the amount of water. And this is the temperature down here. And if you look at these, and we'll just pick one out, we'll pick on potassium nitrate right here. At 0 degrees Celsius, you can dissolve about 15 grams of that in 100 grams of water. But you can see as this is increasing, and we pick on 60 degrees Celsius, we're all the way up to 100 grams of potassium nitrate will dissolve in that. If we go up just 10 more degrees, that takes us to 130 grams. So you can see that potassium nitrate, as the temperature increases, you can dissolve a whole lot more of that in there. And as you look at each one of these, almost every one goes up. Here's sodium chloride right here. That one goes up, but not that much. It doesn't change that much with temperature, but not like potassium nitrate did. But most of these go up, and most of these are solids that are being dissolved in the liquid, except for this one right here. This is a gas, and you can see that as the temperature increases, the solubility of NH3 decreases. So if we had, let's say, 60 grams of potassium nitrate, we could not dissolve all 60 grams of that until we got up to 40 degrees Celsius. So if we were at 20 degrees Celsius, all 60 grams would not go. It would At 20 degrees, somewhere around 32 or so grams would go, and then the leftover would just sit in the bottom. So that brings us to the point of saturation. Saturation means if something is saturated, it has dissolved all that it can dissolve at that temperature. I've got 3 pictures right here. This one is an unsaturated solution, which means that it can dissolve more inside of here. If we put more in, it'll dissolve more. Saturated would be it has dissolved everything that it can. And in fact, you would have this. You would have little stuff on the bottom right here to know that it was saturated, because anything else you add to it, it is going to stay right there. It's going to stay in the bottom. Actually, it'll keep going through a process of dissolving. Part of it will dissolve, but some of this will crystallize and go back, and it goes back and forth. And then finally we get to the supersaturated. This one right here is called supersaturated solution, which is one of my favorite terms in chemistry. Supersaturated, which means that it's actually holding more than it should at that temperature. You can make a supersaturated solution by dissolving some solute in a solvent at a very high temperature and then cooling it very, very slowly. And as you cool it slowly, that solute will stay in that solvent until you either drop a little seed crystal inside of here, and once that happens, then all these will start to come out. That's what's happening in this picture. These are coming out of solution, or if you disturb it at all. And so those little hot packs that you can heat up and they go into solution, then you break a little disc inside of there, they start to come out, and this produces a lot of heat. When it comes out of solution, releases a lot of energy. It's an exothermic process that goes on there. And so supersaturated solutions, they're really cool. You can watch them, they crystallize, and then once they get done, you might even think that they never had any water in them. Finally, there are 3 ways that you can affect the rate of dissolving. That means how fast a solute will dissolve in a solvent. Remember, every time, this is what we want to happen. We need this interaction between the solvent and the solute. These green and blue spheres here represent the solute, and this represents water molecules that are coming. We need to have that contact so that these can be broken apart and separated or solvated or hydrated by the water molecules. So one way that you can do that is you could increase the surface area of the solute. One way you can do that is by crushing it, making it smaller. Don't throw in the big chunk. If you're making lemonade and the Country Time lemonade has got wet somehow and it's a big chunk and you just throw that big chunk in there, it's going to take forever to do that. Another thing that you can do is you can agitate the solution or stir it, because as you agitate it, you are bringing more water molecules to the solute and you're allowing that interaction to happen faster. And lastly, you could heat the solution. By heating it, what you're doing is you're giving more kinetic energy to the water molecules, and they are having more interactions with the solute, and it will dissolve faster. So this is an overall view of solutions that you'll need to know. You can find more information in your book as needed. Have a great night.